Okay, we're recording. So here's where we are going to pick up from where we had left off. I forgot to hold it. Okay. So new kind of topic. We're going to talk about how to visualize multivariable functions. Y'all have seen graphs previously, right? But we're going to have to be a bit more careful at this point in how we understand and think about graphs. So I have a definition written down here. I'm going to momentarily skip. I'm going to come down to the idea of a graph that you've seen before. Y'all know single variable graphs, right? Pictures like this you've seen a million times. Okay, so let me talk first about what does it mean for a point to be on the graph. So here we go, a point x comma y on the graph. What does that mean? Well, the first coordinate, x, of course, typically is the input variable. That's the variable that goes into the function that you're trying to draw a graph of. Okay. And then the second coordinate, you'll notice, it's what comes out of the function. Right? So x is the input, y is the output. The point on the graph has both the input and the output together, making up a single point. And so all together then, the graph is the collection of all points that fit this format, right? Where the first coordinate's the in, second coordinate's the out. Okay, so that's the big idea of what's going on in this definition right here. Let's see here. So typically, if you're going to draw a graph, and we'll talk about how to draw it, what does it look like in a few minutes. But this definition here basically just copycats that idea, right? So a graph is a collection of points, just like it is in the familiar case, right? Where we take the inputs, right, the things that go into the function. Well, but now this is a multivariable function. There's actually a bunch of inputs to be put first. And then, then we plug them into the function. Out comes some outputs. Those outputs, right? Well, there's now a bunch of outputs, not just the one coordinate, but several coordinates in the output. And so again, same deal. You'll notice that this definition is just take all the input coordinates and all the output coordinates, kind of smash them together and make points. Those are points that are on the graph. So this definition is just a kind of I'm going to say a shameless ripoff of this definition right here. Color coding intended to demonstrate the analogy. Okay. All right. So now when you do this, something weird does happen, and you probably haven't thought of it in the past as being weird because you've done it so many times, and when you first saw this, you probably maybe weren't to the age yet where you question everything, you know. But this function that we're looking at, whose graph we're looking at, notice the domain is one-dimensional. There's only one input variable. Notice the target is one-dimensional. Only one output variable. So why are we drawing a two-dimensional picture? Right? There's something a little weird about that we're drawing a picture. It's not in the domain. It's not in the target. It's in a totally different, made-up, manufactured world where I kind of take all the inputs and all the outputs and kind of smash them together to get this world where I can draw the graph. So, heads up, just something to be aware of. Okay, now next observation I want to make. There's a different way to think about a graph. Perfectly reasonable, very useful in some contexts. I like to think of the graph as what results when you take a function. Here's a function. And whatever the values are that come out of that function, set those values equal to a new variable. But I'm going to say this is a new variable because if you look at the actual function, right, you need, in order to talk about a function, you need to give a name to what goes in. The input has to be called something if we're going to have a formula for it, right? So we'll have an x that goes in. What comes out is called f of x. there need not be any y's involved. There was no y that was part of the original function. So I want to emphasize we are choosing. We do not have to. We are choosing to introduce a new variable. We're calling it y just for alphabetic simplicity. And by setting the output values of the function equal to this new variable, we get an equation, and this is the equation of that curve that we call the graph. So think of it in either of these two different ways. It's what you get when you put the inputs and outputs together in single points, or it's the set of solutions to the equation formed by setting the outputs equal to a new variable. Either of those is, well, let me say this, both of those points of view are important, and at any given point you can use either. Okay, so let's apply these ideas now to a new context. Let's look at a function from R2 to R1. Now check it out, a multivariable function, right? There are two input variables corresponding to R2 being the domain. Well, okay, different ways to think about this. Now again, you can take your outputs, set them equal to a new variable. What am I going to call this new variable? X and Y have both been sort of accounted for, spoken for as input variables. So the output, I can't call it Y. So again, alphabetic simplicity, I guess I'll call it Z. It doesn't really matter, right? But let's call it Z. And as a result, I get this equation. And we could say that this is the equation for the graph that we're trying to understand. And that's fine. Very often useful. Here's a different way to think about it. Again, as previously discussed, the inputs, right, R2, X and Y, go first, and then the output, whatever comes out of the function, Z apparently is what we're calling that, comes second, right? And with those inputs and with that output, we get again a corresponding point, that being a point on the graph. Okay, so now let's just think through geometrically what's this going to look like if you do this in this case, two variables in, one variable out. Notice for every point in the plane down here, the function's going to tell us how far to push that up to get to the corresponding point on the graph. So for every point in the plane, there is a corresponding point on the graph. Let me say that a little bit differently. You're going to take this entire plane and lift it up different amounts in different locations, right? But the plane gets lifted upward, asymmetrically, right? To produce this thing called the graph. And I appeal to your geometric intuition. This resulting thing, the dimension of the graph itself, therefore should be the same as the dimension of the domain. Right, so that's why, because we have a two-dimensional domain here, we should expect, and it turns out to be the case, that the graph is a surface, which is an intrinsically two-dimensional thing. Real quick side note, I know a lot of y'all are probably thinking, hey, wait a minute, surfaces are, but they're kind of three-dimensional in a way. You have to distinguish between the dimension of the object itself as compared to the dimension of the world that it lives in. Right? So, for example, think about the surface of the Earth. Yeah, we live in three dimensions. Yeah, of course. But the surface of the Earth, where we spend most of our time, right? That surface is really kind of two-dimensional. Longitude and latitude. If you want to know where you are, you need two coordinates. That makes it intrinsically a two-dimensional thing. Okay. All right. It has area. It doesn't have volume, for example. Okay. All right, so this is the big idea behind graphs. It is a very useful construction in multivariable calculus. It has some pretty severe shortcomings, though. This is a real problem. A couple of real serious problems that we need to worry about concerning graphs. The first problem I'm going to point out, you very often just cannot draw it. Out of the question. Not going to happen. Here's an easy example. Function with 3 input variables and 1 output variable. So here's the equation of the graph. Points on the graph look like this, and, well, unavoidably, check it out. How many coordinates are there for these points that are on the graph? 3 in, 1 out, altogether there are 4 coordinates, which means the graph lives in 4 dimensions, and you can't draw that. Right? Not even make-believe like we do, here, this is kind of cheat that we're using with this picture here, right? It's a 3-dimensional picture. It's not. There's nothing back there, right? I mean, it's on a screen. It's actually a 2-dimensional picture. I'm lying a little bit when I draw this angled axis to make it look like it's coming out of the page. So I have to kind of cheat even to draw a 3-dimensional picture. 4 dimensions, out of the question. Can't be done. Okay. All right, so this is a huge problem, right? A function as innocent as this one, where there's merely 3 input variables, and graph is off the table, not something we can use. Okay, so we're going to need other ways to draw pictures that help us understand functions that are not this construction, because this construction ties our hands too badly. Right? So as a result, this leads to the second problem. Most students in this class, very often students encounter these ideas having never drawn a picture of a function that isn't a graph. And so there is a tendency to conflate the word graph with the function that it's representing. And this is something you're going to have to sort of exert some internal effort to unhabitualize yourself from this idea that you see a picture like this and say let's see here, here's a function which blah blah blah. No, it's not. That's not a function. That's a picture. It's a picture that helps me understand a certain function. That's not a function. So again, we have to make that distinction because not all pictures are going to be graphs. We're going to have other ways to help us understand functions geometrically, as we must. Graphs aren't cutting it. So be very, very careful. You have to kind of police your own language, even your internal language at this point, and make sure that you use the right word to describe the right kind of picture, because the interpretations from those pictures will vary dramatically in terms of making sense of, what do they tell you about the actual function. Okay, so that's a little foreshadowing. Next picture I want to show you, this is not a graph, very importantly, not a graph. This is going to help us understand functions, just in a different way. Right? So the big idea is, I call this the literal picture. I may have made that up, I'm not sure. But I like to call it the literal picture because it's pretty literally just drawing what the objects are that are in the function and what they do. And remember, a function is a trio. Function's 3 things. It's a domain, a target, and a rule of assignment, or we like to think of it as a formula. Right? So the domain, well, I'll draw a picture of it. There it is, the domain R3. I have drawn a picture of R3. The target is R1. Okay, well, here is a picture of R1. And what does the function do? The function takes points out of the input and drops them into the target. And so I'm going to kind of draw at least a representation of that action of what the function is doing. And check it out. I have just drawn a picture that's just documenting exactly what's happening in the function. So thus my choice to call this the literal picture. All right, now let me say some bad things about this picture. There's a lot of disappointments from this picture. I can kind of draw a little something. I can say, well, here's an input point that comes out of the domain, and the output value is going to be maybe a point like that over here in the target, and that does something, I suppose, but this is not a very helpful picture, right? We like these kinds of pictures. We like that because I can see a shape, right? That we have a lot of developed instincts about, what geometric features of the shape tell us about the algebraic features of the function it's representing. So positive slope, right? That's a geometric thing. Tells us about the derivative of that function. That's an algebraic thing. Right? So this picture is awesome. Gotta love it. Right? We're going to have some analogous interpretations for these kinds of pictures when you have a function of two variables. Graphs are fantastic when you can draw them. Right? So where's the picture? Here. Where's the shape? What shapes am I going to look at and develop intuition about? Here, I see no shape. So you're going to be tempted to think this is ridiculous and pointless. Right? Here's the yeah, but. The yeah, but is, look at the function that I've drawn this picture of. 3 in, 1 out. This is the category of function where I've already observed you can't even draw anything for a graph. Right? So apples and apples, this is not a fair fight as drawn. This is a much harder function to represent geometrically. And I was comparing that against much easier functions to represent geometrically. That's not fair. So in a fair contest, graph is just an absolute crash and burn failure to give any picture at all. And we compare that with this, which is a disappointing picture. And in that contest, this one wins. Right? Does that make sense? All right. And this picture does have some really nice uses. So, for example, a very reasonable question, and something we're going to spend a bunch of time doing, is imagine a hypothetical scenario where the function represents something in the real world, whatever it might be. Maybe this represents my location, right? And maybe this represents the temperature at that location, just as an easy example, right? A reasonable question that we might ask, and that we will ask, is what happens if from this point I take off and start moving with some velocity, and as I move with that velocity, well, of course, the temperature is going to be changing. My position changes with time, temperature will change with time, and therefore temperature itself will have an output velocity. And we will very reasonably want to understand a relationship between this input velocity and this output velocity. And there's a whole lot to say about how to do that, but notice we have a picture here of the question at hand. Very natural question. Here's at least a picture of the question. And that's valuable. So don't sell this short. This is a good point of view on drawing pictures of functions. Okay, level sets. Again, there's a bunch of language of the definition, etc. Let me start by kind of an easy example. The big idea of a level set, and you'll see this in the definition in a moment, is that you take your function. Here's the formula for the value of the function. And you set your function equal to various different values and then draw the resulting pictures. Right? So for example, if I set the value of the function, f of x comma y, if I set that equal to 1, I get this equation, x squared plus y squared is 1. Y'all know what that is. Old news, that's a circle. Radius 1. Cool. Okay, what if we take that same function? What if we now set that equal to a different constant value? Let's say 2. Well, that's again a circle of radius square root of 2. Again, y'all know what that looks like, right? So notice then, I have pictures representing the input values that correspond to certain selected output values. Said differently, for each one of these outputs, I'm looking at the corresponding inputs. You might say level sets take output values and produce sets of input values. The act of drawing a level set of what I'm describing here kind of goes backwards through the function in a way. So now let's try to make sense out of that with this this definition here. And let's see if we can get a little bit more on. There we go. Oh, and I keep forgetting. I can always do. You know what? I better not. Okay, so looking at this definition up here, first of all, you'll see the backwardsness of the activity of drawing a level set, represented by writing it as F inverse. Now, this is an abusive notation. It's a little wrong. F inverse kind of suggests that this function's invertible. It makes it look like F inverse is a function. Functions can only have one output. What I've drawn here clearly is a bunch of points, right? So abusive notation. This is not really a function, but it's awful handy to represent the activity of looking at output values like B and being interested in the corresponding input values that produce that given output value. So that's thus this notation here for level sets. And the formula for the level set right here, I think my color coding has kind of gone. Notice that the level set is a collection of inputs for which evaluating the function gives me a given output. So that's all this, symbolism up here means. All right, now a couple things to say about it. I have a different picture here. Right? Let's criticize this picture, compare and contrast, etc. I've drawn graphs on the previous page of a function that has two inputs and one output. The graph was a surface. We love graphs. They're very familiar. Why do I want this picture? But this picture doesn't even show the whole function, right? This picture is telling me something about what the function is doing at these points, and it's telling me something about what the function is doing at these points. But this picture is not telling me anything explicit about what's going on at a point like this. Right? Somewhere in between, there's nothing there. What am I going to draw all of these curves? There's infinitely many of these level set curves. I can't draw all of them. That seems like a pretty big downer. The surface encapsulates everything. Or does it? Let's look back at this picture of a surface. Did I really draw the whole surface? Or did I con you into believing that I drew the whole surface? What I actually drew here, if you look critically, I drew kind of this. And if you look even at the point where I'm claiming that we are representing something, notice it's all white around there. I didn't draw a thing, right, telling you where that point is on the surface. I didn't draw it at all, right? And certainly not, over here. Where is that point? This is a two-dimensional piece of paper I'm drawing on. I can't claim that tells me exactly where a point is in three-dimensional space. I didn't draw anything. So, not exactly a weakness. In fact, I would point out here, in order to try to make sense of what's going on at this orange point, you have to use your three-dimensional imagination, which is hard and also kind of nonsense. Right? Whereas looking at this picture, looking at this orange point, I can say, well, look, it's about halfway in between these two level sets, and here's where the function is 1, here's where the function is 2. It's about halfway in between. You can kind of size up without having to think three-dimensional. So, actually pretty cool. In fact, I bet you've seen level sets many times before. Here's one. right? Temperature maps, no big deal. It's not a crazy idea, right? And each one of these color bands represents the temperature, sort of bands of temperature. Where is it in the 40s? Where is it in the 50s, etc. And if you think about it, this curve right here, that's the boundary between where the temperature is in the 40s and where the temperature is in the 50s. That is, this curve that I've drawn right here is where temperature equals exactly 50. That's a level set. Temperature is a function defined on location. This is what I get when I set it equal to a particular constant, namely 50. Right? So, again, why do they draw these pictures? Why don't they draw a graph of the temperature function for the weather and come up with this 3D model representing? Because it's hard to see. Even if they produced literally a three-dimensional graph, you'd be looking at it on a two-dimensional phone or TV or whatever. So, it's better in this context. Does that make sense? All right. Okay. Here's another example. Let's use, I guess I have to do this. There we go. Let's talk about the altitude function. So, given a longitude and a latitude, namely, given a point on the map, there is a corresponding, what is the altitude of the ground at that point? And I could try to draw a graph of the altitude function. If you think about it, if you were to draw a graph of the altitude function, you'd have height as a function of location. You would actually have a 3D model of the topography, right? So, like if you have like this little sort of hill that I've drawn here, a graph would be, again, a sort of a 3D model of the hill. Okay. So, again, hard to work with, doesn't make much sense, but what I've drawn over here is something I can make some interpretations from. I mean, I can kind of see the hill-ish, it's kind of, sort of, if you use your imagination, right? And you can even kind of make some useful conclusions here. For example, by the way, when they draw what are called topographical maps, or sometimes called contour maps, they basically draw a bunch of lines like this. Namely, they draw level sets of the altitude function. And here's how I use those. And that is, if I am currently here and I want to get to the top of the mountain, I can look at the two trails that are marked on the map. Maybe there's one trail that's like that. Just, going straight to it. Here, let me, like that. One trail's going straight to it. The other trail maybe does something kind of like this. Which of these two trails should I take? I guess it depends on how big of a thrill seeker, adrenaline junkie you might be, right? But for me, I mean, maybe when I was young, right, I might have done this blue path, but not anymore. My gosh, look how steep that looks. Let's say each one of these lines represents 100 feet. I'm gaining 100 feet of altitude over that little bit of a horizontal movement. That's steep, right? So this is one of the nice geometric conclusions that you can get from this kind of a picture. Close together contour lines means steep. Far apart contour lines means gentle, easy strolling, right? So certainly at this point, I'm taking that green path. It doesn't cut through contour lines over very short distances. It drags out the altitude change, right? So, the steepest part probably from here to here. Right? Still, that's a lot more distance to spread out a 100-foot altitude gain than this right here is. So it's not the same as a graph. I can't talk about the slope equaling the blah, blah, right? I mean, it's different, but I get understanding on the basis of the picture. Yep?
Is it kind of doing a dimensional reduction?
Kind of what now?
Doing a dimensional reduction.
It depends. I mean, it's just a different kind of a picture that we draw. So don't think of this as the graph as what we started with and that we produced this from the graph, because I didn't. Right? I had a function. A function doesn't have a dimension. Right? It's just an algebraic object, and then I produced this picture from it. And I'd like the idea of saying that this is a more dimensionally prudent kind of a picture to draw, less dimensionally wasteful, right? Yeah, does that make sense? Yeah, good. Okay, yeah. All right. By the way, here's another one. This is an actual topographical map of a mountain in Colorado, and I have driven this road. And by the way, if you're looking for a thrill, this is the highest paved road in the continental U.S. It goes up to over 14,000 feet, and you can just drive your car up there. The thing is, it's a very, very high mountain, and as you drive along, there are drop-offs that are extremely steep, and there's no guardrails. And you're at 13, maybe 14,000 feet, and your brain isn't working quite right. It's actually pretty scary. So anyway, if you're looking for a thrill. But what I like about this is you can see why did they make the road like this? Why didn't they just make the road go from here to the top in a straight line? Well, same point. You'd be cutting right through those contour lines. That'd be super duper steep. Most cars can't do that. If any, I don't know. Certainly most cars can't. So they do this thing called switchbacks, and you can see the zigzagginess of it all. And what that does is it just spreads out the distance over which you cut through contour lines. And it makes it a lot less steep, and it's, aside from the thrill factor, it's an easy drive. The car does not have to exert, right? You might freak out, but the car is fine. That make sense? All right. Okay. All right. So again, the contour map, very helpful in helping us sort of see that in action. All righty then. Here we go. Well, okay. There we go. Okay, so, neat fact, graphs are a useful kind of a picture to help us understand functions. Level curves, level sets are useful pictures for helping us understand functions. They're totally different kinds of pictures, but they are related to each other in a nice, geometrically simple sort of a way. So, here you go. If you were to draw a level set of a function, and let me do this with the highlighter. If you were to draw a level set of a function of two variables, set the value of the function equal to a constant, different constants at different times. Of course, you draw a bunch of these, but anyway, that's what a level set looks like. The graph, of course, is what you get when you set the function equal to a new variable. Now, that totally different equations, right? Completely different. This one has 3 variables in it. This one only has 2 variables in it. They're very different equations. So, here's the clever observation. If you take a graph and then you do a horizontal cross-section of the graph. Now let's think through before I finish that sentence. Setting z equal to a constant means you're defining a plane, a horizontal plane. And if you were to say, I want to look at points on the graph that are also on that horizontal plane, I say you're taking a cross-section of that graph. And the neat observation to make is that these are the same. Right? So, let's see here. I guess I should, yeah. So, if f equals z and z equals c, then f equals c, just like in a level set. Neat observation. Here's an example of that in action. We've talked about this function right here. We can draw the graph. We can draw a level set of that. Level set is what you get when you set the function equal to a constant. That gives you these pictures here, previously discussed. Now let's draw a graph. The graph is what you get when you set the function equal to a new variable. Again, different equation, very different equation. Momentarily, or well, soon, I don't know if we're going to get to it today or maybe Monday, but I'm going to just assert for the moment that we will soon see that what this equation looks like is a kind of a bowl like that. Details to come later. And now let's talk about what the cross sections of that graph look like. Well, again, cross sections are what you get when you set z equal to a constant. Well, horizontal cross sections, you set z equal to a constant. Those are planes, like so. And as promised and predicted, notice that the level sets, circles, are what are produced when you take these horizontal cross sections of the graph. So again, nice strong connection. Said differently, when you see a connection, this specific connection between graphs and level sets, it helps you kind of buy, I think, the idea that, well, these are very different pictures, but that they're representing the same function. And you can see what they have in common with this idea of understanding, cross sections. Okay. One little minor quibble to this, just as just to clarify technically. Technically, this is a circle in R2. And technically, this is a circle that lives in space in a horizontal plane inside of 3 space. So technically they're not exactly the same, but you know what I mean. Aside from the fact that this one has been suspended in 3 space and this one is in 2, they have the same equation otherwise. So that's why I'm saying they're the same. Okay. All right. Okay, so we've actually now talked about various different ways to draw pictures that help us understand functions. And I have a warning here. Don't conflate these. If you say graph when you mean level set, you're going to have something that's completely wrong. If you say level set when you meant graph, huge problem. It's just wrong, right? And so here's my example to illustrate this. Let's ask, what functions can we use to help us understand this line L? And just to get the ball rolling, I'm going to give you the equation of that line right there. So what functions does this represent? Well, when you want to talk about a relationship between a geometric object like a line and an algebraic object like a function, well, again, you got to be specific. Are we connecting these by way of the graph construction or the level set construction? Or, by the way, real quick, notice that a parameterization, if you think about it, is, again, a connection between algebra and geometry, right? You take a function and then that traces out a curve or or whatever, and it traces out a geometric object. So another connection between algebra and geometry. So what are these specific functions that relate to this line in these ways? And first observation I'm going to make is that we can view this as being a graph of this function right here. Let me persuade you of that, because if I take the graph of this function, and keep in mind graph says set the value of the function equal to a new variable, right? So here I am taking the graph of that given function, right? That's what graph means. The graph of this function is represented by this green equation, which you will notice is algebraically equivalent to the given equation. I've moved things around a little bit, right? But a little bit of algebra 1, and you can totally see these are morally equivalent equations. So they draw the same picture. Okay, everybody on board with that? I emphasize, this picture is absolutely not the graph of 2x plus 3y. It's a graph of this algebraically very different function. Again, you got to kind of follow the rules. Okay. All right, now, where did I come up with this function? It's really not that big a deal. Why did I erase that? I wanted to keep the... it's not a hard thing to do. In fact, the way I did this, the way I got from this equation to this equation, I just solved for y. Notice that if you take an equation and solve for one of the variables, the punchline is some function being equal to that variable. In other words, a graph, right? So it's a nice little hack to remember. You just have to solve for the variable in question, and then you can reverse engineer the function. All right. Okay. Okay, now, how can we represent this same line now, same equation? How can we represent this as being a level set of something? Now, this is a totally different construction, right? Again, level set construction, graph construction, totally different. It's not going to be the same function. Okay. Let's see, making a level set, I'm going to have to figure out what function can I set equal to a constant to produce that equation. Oh, that's an easy one, right? I can see it right here in the, that is what I set equal to a constant. Namely, that is the function whose level set gives me that equation, namely this line. All right, so sometimes the fish just jump in the boat. This one was all, in some sense, the algebra was already done for us. If it hasn't been already done for you, if you need to kind of make this happen, like if you have some equation that looks like a bunch of stuff equals to a bunch of other stuff, how would you do the algebra? How would you figure out what this is a level set of? Notice in all such case, any equation, you can always take what's on the right-hand side and subtract it over to the left-hand side, which will then give you a bunch of stuff equals 0, which of course is a constant, and then you can take advantage of the same trick. So, nice little hack. Okay. Now, very different functions. Aside from the obvious, these two functions, they obviously have different formulas, right? These two things are not the same, but that's not the whole story. Not only are they different formulas, they have different domains. They have different numbers of variables. They are very, very, very different functions. Does that make sense to everybody? And one thing we're going to find, we're going to very soon be starting into what I like to call the calculus of different kinds of pictures. Y'all have already seen in your Calc 1 class, or single variable calculus, you've seen what I like to call the calculus of graphs. Right? When you do derivatives of a function, what is the geometric interpretation on a graph? Right? We are soon going to see the calculus of graphs of multivariable functions. That's going to be a little different. We will then, shortly after that, see the calculus of level sets. And the calculus of, the calculus of this function and the calculus of this function, now they're both going to tell us something about this line, but they're going to tell us different things about this line. And so if you pick the wrong function and apply therefore the wrong kind of calculus, no surprise, you're going to get dramatically wrong answers. So these distinctions, I know it kind of seems silly, and I want to grant that getting uptight about the language and everything, it seems a little silly, but this is all that will protect us against just getting dramatically wrong answers that we otherwise wouldn't even know why we were getting dramatically wrong answers. So very, very important stuff. Okay, lastly, how do I parameterize this line? What is the function, right, that relates to this picture by way of this idea of parameterization? And this is, you may recall, something we've talked about previously, and I'm going to make the observation that this is a point on the line, And then I can look at this difference vector. That difference vector is a vector parallel to the line. Right? And you can see that point and that vector and how they show up in the usual way with the how you make a parameterization, 0, 2, thus this 2 right here in purple, and then plus t times that green vector, which gives me the 3t and the minus 2t. So old news, y'all already know how to do that. But again, I emphasize this is a very different function from the ones that we've seen previously. It's not at all the same. In fact, here, let me be more careful about this. This is a very different function from those that I've seen previously. So, no surprise, we're going to see a calculus of parameterizations, which will be different from the calculus of level sets, which will be different from the calculus of graphs. So, lots of geometric sort of interpretations to follow. And again, I emphasize that's why it's so important to distinguish between these different constructions, and accordingly to use the language carefully, right, accurately, right, and appropriately. In fact, let's take one last look at this question here. If this were an exam question, and it'd be stated in a more sort of like directed way, if it were, but and you can find such examples on my old exams that are posted. And hunt through there, you'll find actually quite a few of these. What's challenging about the question? It's not the algebra, right? This process is trivial. Any Algebra 1 student can do that, right? This algebra here, even more trivial. I mean, anyway, plenty trivial, right? So what these questions are about, and accordingly how they will be graded, is not whether or not you did some of the relevant algebra. They're going to be graded based on whether you have made a precisely correct, appropriate use of the language and interpretations of the language. Right? So, for example, a lot of students would look at this and say, okay, well, yeah, but I'm just going to say 2x plus 3y equals 6 because that's what we're setting it equal to. And so some student, why, that's the weirdest 2 I've ever made. I don't know what happened there. Some students would just write this down and be like, yeah, okay, there you go. That's the function whose level set, blah, blah, blah. Okay. But if that's not there, in other words, if this is all you've written down, notice you've just recopied the question, for one thing. You didn't do anything. Secondly, notice another thing. This that you're claiming is the function who blah, 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 this is not a function. Right? This is an equation that says that this stuff equals that. That's not a function. So this is nothing, there's nothing on the page here, looking just only at this alone, right? There's nothing on the page that I can confidently interpret as demonstrating proficiency with the relevant idea, namely being able to make a strictly proper interpretation of the language. So sadly, this wouldn't get any points because it doesn't answer the question. Does that make sense to everybody? I just want to make sure everyone gets, fairly, heads up on what we're going to be looking for on these kinds of questions. Okay. All right. So we've actually already talked through all of this right here. The whole point is that the calculus of these different kind of pictures is going to be different. So we'll draw a line right here and call it a day and pick up here on Monday. Y'all have a great weekend. See you later.
Thank you.